computer. Good, very good. Go ahead.
Okay, good. So thanks for the invitation. So I'm quite excited to tell you about this very recent work on the entropy scaling law and the quantum marginal problem. So let me begin by flashing this example that you are probably all familiar with. It's high temperature superconductivity. And as you may already know very well, even though this phenomena was discovered experimentally in the 1980s, still, I think it's fair to say that there's no general consensus, like the BCS theory of superconductivity, on what the underlying microscopic mechanism is. And part of the reason behind this is because even though writing down toy models of these systems in simple terms is relatively straightforward, and although many people agree on the model, you cannot actually solve these models either analytically or by using a classical computer, at least if you go to a sufficiently large system size. And this difficulty is not just a problem of high temperature superconductivity, but for all sorts of strongly interacting quantum many-body systems that appear in nature. So there's a huge industry of physicists and quantum chemists who are interested in building new tools to efficiently simulate these systems on a classical computer. So one might hope that because the physical systems that appear in nature is local, by which I mean you can express the Hamiltonian as a sum of terms that act on a bounded region of space. For instance, here you have an interaction term that acts on these four particles, 3, 3, 3. So you might hope that this can somehow give you an advantage in solving these problems, as opposed to a like arbitrary Hamiltonian that lives in the many-body Hilbert space. However, Gitaev showed in sometime in the 1990s that calculating the ground state energy of these Hamiltonians is basically hard, even for a quantum computer. And since then, many computer scientists have worked on generalizing this proof. And essentially, right as of now, the state of the art, in the state of the art, you can actually reduce the hardness to the problem in 2D. So if you have like a 2D, like locally interacting system, even then calculating the ground state energy is hard, even for a quantum computer. So this shows that for solving these systems, really locality is not enough, and you need to impose extra physical constraints to be able to make progress.
Sorry, Isaac?
Mm-hmm.
So this statement of the calculating the ground state energy being hard, there are some within some error bars, right?
Yeah, with
what are the
1 over
errors?
polynomial. Yeah,
1
it's
over poly. Okay.
1 over poly. So it's a reasonable error bar.
Thanks.
Yeah. But there's a success story, a well-known one actually, and this is a problem of solving 1D systems with a spectral gap. So imagine you have a set of qubits arranged on a line, and you have locally interacting terms like a nearest neighbor term. And you're promised that in the thermodynamic limit, the gap between the ground state energy and the first excited energy remains as a constant. So it's bounded from below. And there's a very well-known algorithm by Steve White, which is known as density matrix renormalization group, which doesn't work provably, but it works very well in practice. And in 2013, people actually found a provable algorithm. So in both practical sense and in a very rigorous sense, I think it's fair to say that 1D systems that are gapped is easy to solve on a classical computer. So the fundamental insight behind these past works was the area law of entanglement. So Hastings showed that if you cut the 1D system into half, assuming that that it is gapped, then he could show that the Renyi alpha entropy for alpha strictly less than 1 is bounded by a constant. So this suggests that even though in principle you could have had a like an extensive amount of entropy in principle, this shows that for these systems, in some sense, the underlying state is very weakly entangled because the entanglement is only a constant across any cut. Indeed, Hastings was able to show that from this area law that the ground state can be well approximated by an ansatz called tensor network matrix product state, which morally looks like this. So I won't go into the details on what this means, but for those of you who know about tensor network, you have a basic idea on what this diagram means. And the fact that you,
Sorry, so the fact that this was proved, that Hastings proved that you could represent them using MPS, matrix product states, why doesn't that say that we have an efficient algorithm? Why did we have to wait until 2013?
Good question. So this thing you can think of as tensor with a bond dimension that is polynomial in the system size. So you still need to let's see. So even though the number of parameters is like scales polynomially with the system size, if you try to find the global energy minimum within that space, and if the global space is very non-convex, then it could take a very long time to actually find in a brute force way. So to actually find an algorithm that minimizes the energy, you need to be a bit more smarter than that. Indeed, these like provable algorithms, the way that works is that they show that if you apply some operator on this ansatz, it converges to the ground state very quickly. So as opposed to like finding it in a brute force way. So you need to use some extra structure to actually come up with an efficient algorithm.
Thank you.
Good. So an important question is what happens in higher dimensions. If you don't have a gap, then it's really difficult. So I'll keep the gap assumption, but I want to generalize it to dimensions larger than 1, like in 2D. Excuse me. So there's a consensus in the community on what one could do. So like in the 1D case, the consensus is that perhaps a constant spectral gap implies area law like this. And indeed, there has been some partial progress recently by Anurag Anshu and David Gossett, although like they weren't able to precisely establish this. And maybe once you prove that, you may conclude that the ground state can be well approximated by some 2D tensor network. And maybe you can do some extra work to find an efficient classical algorithm. So this is an important problem, but I just want to say that there are some challenges because it turns out that the class of states that obey this area law, in the sense that the entropy is upper bounded by area, and the class of 2D tensor networks, by which I mean PEPs in 2D, can't be equal to each other because what these guys showed is that the class of states that obey area law is much, much larger than the class of states in the 2D tensor networks. So I just wanted to mention that. Okay, so this results like this shows that there is some inherent difficulty in this problem. So this is the point at which I will wear my physicist hat and make an assumption which is perhaps not provably correct, but something that we expect to be true, at least in many large class of gap systems in 2D.
Quick question, sorry. Can you provide some intuition to what are these non-PEP states that are area law? Like how should we think about them?
So I must say I'm not completely sure if there's an easy way to explain this. It's mostly because I don't have a very, very deep understanding of this paper, but I believe what they're essentially doing is that they write down a wave function which manifestly obeys the area law, but it's expressed in terms of some function. And I believe their main point is that the number of such functions, which all gives rise to different states, is too large compared to the number of parameters that the 2D tensor network quantifies.
So it's a counting argument, basically.
It's a counting argument at the end of the day.
Thank you.
Okay, so I'd like to make an assumption, which I would like to call as the strong area law. So in the previous slide, when I said area law, I meant that the entropy is upper bounded by the area. But as many of you may already know, you can actually calculate this thing either using field theory methods or in exactly solved models. And these people have shown that if you do that, the entropy is not just upper bounded by the area, but it can be decomposed into two terms. One, which is non-universal, which depends on the microscopic details, which are basically the entanglement across this cut. And there's a sub-leading term, which is universal in a sense that it is insensitive to small changes in the microscopic physics, unless you move into unless you close the gap. So this is not proven at the mathematically rigorous level, but just take it for granted. And the main message of this talk would be that if you believe that this equation 1 is correct, then we can use this to dramatically reduce the complexity of the classical simulation. And let me just point out that for those of you who are not familiar with this equation, I just wanted to say that this equation may look very special, but it's really not, because there has been many studies, especially between like 2010 and 2015, in which there was a whole boom of calculating this entanglement entropy numerically and analytically. And these results corroborate this formula. But having said that, you can come up with some weird counterexamples which breaks this scaling form. I can tell you more about that later in the talk.
Sorry, another question. Breaking the scaling law, you mean some sort of a fractional power? What else would you expect?
So ultimately, what I care about is that some linear combination of these things cancel out this term as well as that term. So I will show you an explicit linear combination of entanglement entropies, which I would like them to vanish. And they no longer vanish in some counterexamples.
But is there some general principle that we expect S of A to be an analytic function of A, that it could just expand and there are no like there are no fractional powers, like square root A?
Oh, I see. So yeah, I don't know if there's any such argument, but the example that I have in mind, these are like lattice models. In lattice models, you can do all sorts of very funny things locally. So you can break things locally. I should mention that the constraints that I need to be satisfied, you can make them satisfied by simply deforming the subsystem. But
okay,
yeah, I think yeah, but it's yeah, we can only deal with these things in a case-by-case basis at the moment. Anyway, so I'll be very vague here and just like I'll be more precise in the later part of the talk, and I'll just tell you vaguely what our main result is about. So I want to claim that if you believe that this this global state satisfies this formula, then you can use this to find a solution to the quantum marginal problem. And that was part of the title of the talk. So I want to first explain what the quantum marginal problem is and why it's relevant for simulating these systems on a classical computer. So let's start with the marginal problem, or the classical marginal problem. So normally, when you think of probability distributions, you're given a valid probability distribution, and you are maybe interested in calculating its marginals. But in the marginal problem, you're in an exactly opposite situation. What is given to you are marginal probability distributions, which could be anything, literally. So in this case, we have marginal probability distributions over xy, yz, and xz, 3 random variables. And the question that you're trying to answer is whether there's a global probability distributions over x, y, and z, which is consistent with these 3 data. And of course, such a probability distribution may not exist. In particular, if this guy and this guy over the marginal of y yield different marginal distributions. That you could certainly write down those things, and in those cases, you won't have a consistent global probability distribution. But if such a thing exists, we say that these marginals are globally consistent. The quantum version of the marginal problem is fairly straightforward. You replace all the probabilities to density matrices. So in this case, what is given to you is the marginal density matrices over xy, yz, and xz. And you ask whether there exists a probability density matrix over x, y, and z, which are consistent with all these data. And again, if such a thing exists, we say that these marginals are globally consistent. And in these both classical and the quantum marginal problem, you're trying to answer this in a many-body setting. So you might be wondering.
I have a simple question. So what does x, y mean? Is it the union of x and y, or what does it mean?
Yeah, it's x union y, right?
Okay. Thanks.
Yeah, throughout this talk, I will use this notation. So I will suppress the union notation. Thanks. So the reason why this is relevant for the many-body Hamiltonian is because the physical Hamiltonians are often sum of local terms. So here x, this is a summation over the supports of each of the terms, and x would be localized for physical Hamiltonians of interest. So the ground energy, which is in principle a minimization problem over this exponentially large space in the system size, can be potentially rewritten as a minimization problem over a set of reduced density matrices, which are in some sense only of which are in some sense can be described by polynomially many number of parameters, provided that you can actually check that these guys are globally consistent. And of course, if it was as simple as that, everybody would have been using this approach, and this doesn't work in case it wasn't too obvious to you. Because the real question is, can we actually efficiently check if these reduced density matrices are consistent with each other? And this is a real hard problem. And this problem actually goes way back. At least it could go even, it could be even older than this, but the earliest literature that I could find was in 1959. So this guy is Charles Colson. He's one of the first quantum chemists in history, and he was famous for elucidating the structure of benzene. And he noticed even back then that for the purpose of calculating the energy of a many-body like a chemical system, it suffices to know the two-body density matrices. And the only difficulty seems to be that we don't know the set of conditions under which these guys are consistent with some local state. So he was hoping that perhaps there would be a nice solution found in the future. But in the quantum case, there is a difficulty, and one difficulty is the monogamy of entanglement. So suppose you have two states, two marginals, let's say over AB and BC. Let's imagine A, B, and C are all qubits. And let's choose these marginals to be maximally entangled states. So clearly, if you trace out A and trace out C here, then you get maximally mixed state over B. So these two are consistent over B, but there cannot be a global state consistent with both of these, because that would violate the monogamy of entanglement, because B, if such a state exists, B would be simultaneously maximally entangled with both A and C, which is impossible in quantum mechanics. Now, contrast that to the classical case in which, well, slightly more generally, if two density matrices commute with each other, and if they're consistent on their joint support, then you can simply write down with this global probability distribution or density matrix, which is consistent with both AB and BC. So the fact that the quantum problem is hard, even in this very restrictive setting, suggests that in the many body setting, the problem will be significantly harder. But since then, since quantum information started, people began to have a more refined understanding on why this problem is so difficult. It turns out that if that's all the assumption that you have, if you're only given a set of reduced density matrices, then generally speaking, for checking the global consistency, this problem is hard even for a quantum computer. So there's basically no hope to find a general condition under which there exists a consistent global state. And Mary Beth, who's famous for proving the strong subadditive of entropy, she was I went to a workshop on the quantum marginal problem, and she told me that she's lived long enough to see this happening, and she said some scientists work on the quantum marginal problem, and they basically give up because it's impossible to solve, and then they disappear from the academia, and then new generation comes over and makes the same mistake again. So while she was obviously joking, what she said was not exactly untrue. But with the help of quantum information recently, there are some special conditions which are found. So I should emphasize that these are special conditions because you cannot possibly hope to find a general sufficient condition. So I guess there's no like logical inconsistency here, but the real question that one should ask is whether these conditions are applicable to any physical system that we actually care about. So that's what I'm gonna, I'd like to tell you about the nature of these conditions and how they are related to the physical systems that we want to study. So just to give you a perspective, if you have a many body system, you can, broadly speaking, write down a set of marginal density matrices, which may or may not be consistent with each other. But the kinds of things that we actually care about are the marginal density matrices, which are actually consistent. And moreover, we want to be able to verify that efficiently. So this is the set that we really care about. And we don't have a complete characterization of this set. But we do know a very specific example, and that's the mean field ansatz. So if you have a reduced density matrix over 1, 2, all the way to n, obviously their tensor product is consistent with some valid quantum mechanical state, because this is just a quantum mechanical state. So everybody knows that. And the new solution is strictly beyond the mean field, in the sense that one can actually prove that the sum of the solutions that you can write down cannot have a mean field expression. Moreover, I will argue that these solutions are actually physically quite relevant. And they can be potentially useful because there's a linear time algorithm for computing the energy and the entropy. Okay, so I'm being a little bit more precise on what this condition is, but still like glossing over the details. So the condition, roughly speaking, looks like this. So what is given to me is a marginal density matrix on a bounded region. And internally, within that marginal density matrix, I will enforce two things. One is that it is translationally invariant. I just wanted to emphasize that I'm not saying that the global state needs to be translation invariant. I don't need that assumption. I merely assume that the local density matrix is translationally invariant. And I will assume that within that small patch, this area law holds. Okay. So the point that I'm trying to make is that both of these conditions, although the second condition is somewhat vague at the moment, both of these can be verified explicitly in a constant time because you're considering a constant size subsystem. And if these conditions are satisfied, then there exists a global state which is consistent with all the marginals. To be more precise, there exists a translationally invariant state on an infinite lattice, which is consistent with this density matrix everywhere. And the key idea behind how this works is what is known as the quantum Markup chain in the literature. So let's say you have a tripartite quantum state, rho ABC, and suppose this linear combination of entanglement entropy vanishes.
Sorry, quick question. Can we go to the previous slide? So the density matrices you're considering is basically the same density matrix moved around.
Right, that's right. Translated in both X and Y direction.
So I guess I'm missing some point. When you said this, the global state is not translational invariant? What did...
Oh, I'm saying that I'm not assuming that.
Ah, okay. I see.
And
one more thing. Yeah. So there's a version of, I guess, a simpler version of the marginal problem, which is if you assume that you're looking at n marginals, and the question is that whether they would fit inside the pure state.
Right.
Could you make progress on that problem as well? Is that related to this? I mean, it could be translated to this, right?
It seems hard to use our method to make progress on that.
Because in that case, there are a bunch of inequalities that are known that you should satisfy, right? For the eigenvalues of the density matrices.
So if you want the global state to be pure, I think our solution is agnostic to the purity of the global state. So I don't think it will like tell you much about it.
I see.
So if I'll get to that later, but the point is this is applicable to mixed state as well.
I see. Thank you.
Okay, so anyway, so the key idea is to use what is known as the quantum Markup chain, and by the strong subadditivity of entropy, this linear combination is lower bounded by a larger or equal to 0. So the fact that this state is exactly equal to 0 means that the underlying state is very special. And what Pet showed is that indeed, if this linear combination is equal to 0, this state is special in a sense that you can begin with a marginal, let's say over AB, and apply some linear map acting on B, and this way you can recreate the global state. Or alternatively, you may begin with a marginal over BC and apply a map on B to create the global state. Obviously, not many states can have this property. Not all states can have this property. And by using this fact, it turns out that you can, in some sense, merge quantum Markup chains. So what I mean by that is that suppose you have two states, rho ABC, lambda BCD, such that both are Markup chain in their respective way, So rho ABC satisfies this constraint, and lambda BCD satisfies a similar constraint. And suppose they are consistent on their overlapping subsystem, which is like BC here and the BC here. Then we can show the existence of a 4-part type quantum state, which is consistent with rho ABC and lambda BCD. And moreover, this state, this new state, is actually again a Markov chain. So a bit of a cartoonish way of saying this is that if you start with 2 Markov chains, you can somehow merge them together to get a Markov chain on a larger space. So this is a bit abstract. So I just wanted to tell you how this works in our particular setup.
Actually, sorry, a quick question. I guess I'm not understanding this lemma in 2016. Why doesn't this follow from Petz's work?
It does follow from Petz's work, but it's a useful lemma that I wanted to emphasize.
I see.
Mm-hmm. So the setup is this. So I will consider a 2D many-body system, and I will coarse grain the system sufficiently many times so that this area law holds up to a very good approximation. In this talk, I will ignore the approximation error, and I'll assume that the area law holds exactly. And the way this works, roughly speaking, is that you begin with this area law assumption and a constant size patch, and then you deduce that locally certain linear combination of entanglement entropies vanish, like these 3 subsystems here and like these 3 subsystems here. And I should emphasize that the important thing is really these 2 conditions, not that, but this is just to give you physical motivation or justification on why you should expect these identities to hold. But whatever the case may be, this is something that you can verify locally. And by combining these two conditions, even without using this equation at the larger scale, you can deduce the existence of another state, which is supported on a larger region, a union of this guy and that guy, which is again a Markup chain. So schematically, you can sort of bootstrap this argument over and over again. And here's a kind of a caricature of what's going on in the proof. So you begin with small Markup chains to create a larger Markup chain, and you combine larger Markup chains to create even larger Markup chains, and this process goes on. And an important question that you should really ask is, okay, you can use this Kato et al.'s lemma, but how local can you make the Markov chain assumption? Because like, in order to use this argument, you need to actually verify this assumption. And if verifying takes a long time, then that's not going to be very useful. And there are 2 situations that you might be worried, that you might be keen on considering. One is the situation in which you have only a handful, like 3 Markov chains, from which you can you want to reconstruct the global many-body quantum state. So this on the right-hand side, you can view this as some many-body quantum state. This is not a situation that you want to be in, because on the right-hand side we have a many-body system. So at least one of these 3 Markup chains must be must be a condition on a many-body quantum state. And verifying the Markup chain condition won't be easy in that case, because you need to calculate the entropy, which is generally not very computationally intensive. A better situation that you want to be in is that you have Markup chains, like tiny bits of Markup chains that are sprinkled around. And somehow you can combine all these things to deduce the existence of a global state. So fortunately for us, we can actually show that it's really the latter case on what's happening. Good. So now we finally have the concrete conditions. So even though I use the area law as like a guiding principle, guiding justification behind this condition. Ultimately, what really matters are these conditions. And this notation looks a bit strange, probably to many of you. So I'll explain what this means. So let's start with the simplest one. So so first of all, the condition is over a density matrix on a 3x3 system. So each of these squares, you can think of them as finite dimensional quantum system, like qubit or qubit. So you have like 9 such particles. And when you see a gray square, like here, that means you're tracing over that local degrees of freedom. So this would be the reduced density matrix over these 1, 2, 3 white squares. And this, sorry, it'll be the entropy of that. And this will be the entropy of the reduced density matrix over these 2 little squares. And we didn't need to specify their absolute locations because we assumed that the marginal is internally translationally invariant. And ultimately, the main result, which is agnostic about all this area law physics motivations, is that if these conditions are satisfied, then there is a translationally invariant global state on an infinite lattice, which is consistent with the marginals on the 2x2 clusters everywhere. So that's the key result. Let me just comment that you can verify that these equations follow from the area law. And in fact, you can even satisfy volume law contribution and still verify that these conditions are satisfied. So, and the volume law case corresponds to the finite temperature case. And in that case, what you want to minimize is not the energy, but the free energy. What's cool is that it turns out that you can actually also upper bound the free energy because you can find an exact expression for the maximum global entropy, which is compatible with the marginals that satisfy the constraints that I described in the previous slide. So if you take the thermodynamic limit, then the entropy density reads like this, using the same convention as I described in the previous slide. And I think this is really cool because it's a closed form expression. And entanglement entropy of a many-body quantum state, it's often not very easy to write down in a easily computable closed form expression. But because of our condition, you can actually do that in our case. But coming back to the
quick question about the previous slide. Sorry, this maximum global entropy, is this like a Jane's entropy or?
This is like Jane's entropy. But remember that we don't have, we have not just constraints on the local expectation, on the marginal local expectation values, but we also are imposing we're also enforcing the marginals to obey these local Markup chain conditions, and that lets you derive this.
I see. Thank you.
Yeah, but coming back to the ground state picture, the area law picture. So I just wanted to briefly talk about the physical applicability of this result. So if you believe that all 2D translationally invariant gap phases satisfy area law, then they should also satisfy this condition. But the question is, do you really expect that to be true? A worry is that there are 2D gap systems with so-called spurious contributions to the area law. So Sergei Bravy had this counterexample, and since then, people have written papers about generalizing these counterexamples, which you can verify to violate our assumption. So one might be worried because these systems are explicit systems, gap systems, in fact, in 2D, which violate our assumption. So you might think that's a problem, But at the end of the day, the way in which you're going to use these is to use them as a variational onsets to minimize the energy. And because you can create these things by a finite depth quantum circuit, you can also remove them using a finite depth quantum circuit. And in the Heisenberg picture, this amounts to simply changing one local Hamiltonian to another local Hamiltonian. I guess what I'm trying to say is that I am unaware of any example in which you can, so it looks like up to this like a local depth, finite depth quantum circuit in 2D, it looks like you can always cure this spurious entanglement problem. So the big question that I'm always very curious about is, does this really cover all possible 2D gap systems? I don't have any counterexamples, but it'd be good to know whether this is true or not. So it's just a food for thought. Yeah, so
quick question again. I'm confused about the interpretation of this Cato result. So you're drawing, you or them are drawing a connection between this area law in 2D and Markov states. Now, the physical interpretation of Markov states for a tripartite system is that if B is in the middle, A and C do not have genuine quantum correlations, right?
That's
the correlations
right,
are mediated through B. The fact that we're saying that we expect this area law in low energy of quantum systems, we're certainly not saying that we expect the Markov property, as in like there are no genuine quantum correlations between these regions and low energy states of 2D, right? That seems too much.
Like these conditions will not be satisfied exactly. So like up to good approximations, we expect them to be satisfied. And in that case, you can derive bounds, but the analysis becomes much more complicated. But I agree that these conditions, they won't be satisfied exactly in practice.
So just a little violation of these conditions is the room for all the interesting correlations in low energy states of 2D, is responsible for all the interesting correlations in low energy 2D physics, basically.
Sorry, can you say that again?
The fact that the states are near Markov, this is basically saying that near the low energy states that appear in 2D local Hamiltonians with area law are near Markov. That's already also pretty surprising, right?
I think, but that is a logical consequence of the area law assumption.
Thank you so much.
Okay, so I wanted to tell you about a toy example that tells you what's going on in these papers. And for that, I really wanted to consider like the minimal possible non-trivial examples. And surprisingly, the solution is actually new to the best of my knowledge, even in the classical case. So even the classical example in which the marginal density matrices all commute with each other is quite interesting. So let me do that in the remainder of this talk. So although I was talking about many body system, imagine your like quote unquote many body system is just a 3x3 system. And the marginals that are given to you are these like a 2x2 matrices, like here, 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 here. Sorry, I didn't mean 2x2 matrices. Density matrices on 2x2 subsystems, and assume that the probability distribution, the density matrix is classical. So both the marginal and the global data is classical. And within this toy example, I have a slightly simplified assumption. So you might remember these conditions from the previous slides, but these are the first two conditions. So I will claim that if these marginals, these four guys, they're translationally invariant, and if they satisfy these Markov conditions, then they are consistent with these this probability distribution over this 3x3 thing. The underlying idea that is applicable to this toy example, but also to both the quantum and the classical case in the many body setting, is the inclusion-exclusion principle. So this is a simple fact that says that the cardinality of A union B union C is equal to the cardinality of A plus B plus C minus the A intersection B, B intersection C, and plus A intersection B intersection C. And you can generalize to the when you have like n sets. So what I would suggest you, if you're interested in like following these proofs, is to first write down the log of the probability distribution in the spirit of the inclusion and the exclusion principle. It's something that you can write down, and so I can't explain how I came up with this, but let's say this is given you as a hint on what to do. So in that spirit, we can consider this object, like imagine writing down the global log of the global probability as the log probabilities in the spirit of the inclusion exclusion principle. Okay, you can do that. But there are two questions. So once you exponentiate both sides, obviously what you get here will be some non-negative thing. But first of all, it's unclear if this p tilde is normalized. So it's unclear if this is actually a probability distribution. And secondly, it's not clear if p tilde is actually consistent with the marginals. And the main claim of this short exercise would be that with the conditions that are imposed on the marginals, you can prove both statements. So I've done the exponentiation for you, and here I have the expression for p tilde. So how do you proceed? And it's very simple. What we do is that we simply use our assumptions. There's a very simple fact known about the random variable, 3 random variables that obeys this constraint, and it's that the global probability distribution can be expressed as follows. And this is a special case of the PETS map that we briefly discussed in the beginning part of this talk. So if you just plug that in into, say, this expression, you'll find that the probability distribution obeys this identity. Okay. In fact, because we impose 2 constraints, we will get 2 non-trivial identities on the marginal probability distributions. And we'll be able to use them in a non-trivial way. So again, we have this p tilde, and I've written down a cheat sheet for you so that you can use them. And as I would like to first show that this is a valid probability distribution. So let's sum over the random variables on the top row from the right to the left. So focus on this guy. So I simply remove this p tilde because that's not too relevant. And so I'm tracing out or taking a partial sum over this random variable. And once you do that, if you stare at this thing, you see that you have a marginal probability over these 3 white squares. And you can replace that by using this first formula. And you can see that, in fact, this guy actually cancels out with here, this guy, and that guy. Okay. So by making use of that identity, you can reduce p tilde to this guy, at least after you sum over this square. And then take a partial sum over these remaining 2 white squares, and what you get is this. The point is this guy is equal to that guy. So now you have a Markup chain over the first 2 bottom rows, which is obviously a valid probability distribution. So therefore, if you sum over everything, you get 1. And therefore, p tilde is a valid probability distribution. Moreover, by either like summing over these two squares or these two squares, you can see that the marginal probability of p tilde is consistent with both this guy and that guy. And you can repeat the same proof while rotating everything by 180 degrees to conclude the same thing about the remaining marginals as well. So the conclusion is that under our assumptions, this p tilde is a normalized probability distribution consistent with all the given marginals. And you can also write down an expression for the entropy because it has a very nice factorized form. Maybe not factorized form, but it's a linear combination of log of the marginals. So you can use that to write down the exact expression. And of course, you can simplify that using the translational invariance condition. An interesting fact that you can prove is that this is actually the maximal entropy compatible with all the constraints we have specified. So the reason why I'm saying this is because even though this expression, it is indeed the expression for the entropy of p tilde, for calculating the free energy, you want to minimize the free energy. And that means that you want to minimize the, you want to maximize the entropy. So the maximization is important. And in some sense, this is automatically done for you because one can, by using the strong subadditivity of entropy, this is the maximum that you can achieve. So if you were to variationally upper bound the free energy, you can replace this minimization problem, which is a very expensive because you have to calculate the entropy and the energy. You can replace it to you can upper bound that by an easier minimization problem wherein both the energy and the entropy can be computed. So in this case, the cost saving that you get is from d to the 9 to like order d to the 4. But in a many body setting, obviously the improvement is much more significant. Yeah, so that's what I just said. In the many body setting, you get a better improvement. Okay, so that was only a classical case. I won't have much time to discuss what's going on in the quantum paper. And the way I think about it is that the classical case is like a cute exercise that you can do to understand what's going on in the quantum case. But in the quantum case, things are very complicated because basically nothing commutes with each other. So all these like nice objects that we defined should be generalized in an appropriate way because when you reorder the density matrices, like you often end up getting a different expression. So the very process of correctly ordering them can be quite cumbersome. So, but at the end of the day, I just wanted to say that what really saves us are two things. One is the fact that if you have two different recovery channels, they commute. So what I mean by this is the following. So here I have this weird notation. What I mean by that is that I begin with a density matrix over these 4 squares, and I'm applying a PETS map corresponding to these like left 4 squares. And then I apply a PETS map corresponding to these like right 4 squares. And because these two marginals, they are supported on disjoint supports, you can commute these two PETS maps. So that's kind of the trivial identity that you can get, which you can exploit. Even though the density matrix themselves don't commute, as long as the density matrices are far away from each other, their PETS map commute with each other. A somewhat less obvious identity is something that looks like this. The interpretation of this formula is that you begin with a density matrix over these four guys and apply a PETS map over these 4, defined by these 4, and then apply PETS map defined by these 4. And it turns out that in this case also, you can commute these two. However, this identity is much less much more non-trivial because this pets map and that pets map can in principle, they may not commute with each other. But, and indeed, indeed, they may not commute with each other in practice, but the point is at least applied to this particular state, their action commutes. So we can, the way it works is that you begin with a small subsystem size, like a subsystem size of 4, and you find all the relations that are inherited from the area law. And you try to build up the global state this way in a consistent way. And if you succeed, then you're done. But if you don't, then you increase your subsystem size and try to incorporate more relations. And it's kind of amazing that this algorithm actually halts in a constant time. But I guess if you're really interested in the proof, like this is how the proof was constructed.
Sorry, Isaac, can we go back to the last slide? Yeah, right here. So in the mathematical physics community, Petz actually himself, one of the ways that he talks about the Petz map is through these projections to subalgebras that are, I mean, technically they're called conditional expectations. And you would say a state is a Markov if the conditional expectations commute. They form a commuting square.
Right.
So that looks like your condition 1. Am I right? Am I understanding this correctly?
I would say condition 1 is a trivial thing. So let's say, let's call each of the columns as A, B, C, D. So that's A, B, C, D. What this is merely saying is that the recovery channel acting on AB and the recovery channel acting on CD commute with each other. So that's a trivial statement.
Yeah, that's a trivial statement. Yeah. So I guess it's more like 2.
Yeah, 2 is the non-trivial statement. And it's non-trivial in many ways because okay, so maybe this is not the best example to explain why this is so non-trivial, but it turns out that there are relations in which you don't have a commutation relation between channels even on a particular state. It's just that you simply have relations between 4 channels. So you have like channel 1, 2 and channel 3, 4, and they are all different from each other, but the action on channel 1 and 2 is equal to action on channel 3 and 4, acting on some particular state. So these are like really subtle statements that are not even about the equivalence between channels. I mean, I guess it is an equivalence about channels, but on a particular state, and it's not about the commutation relation. It's something much more subtle.
But am I understanding this correctly, that condition 2 here is a necessary and sufficient condition for a Markov chain? It's definition. Could be used as a definition.
I think at the end of the day, in a convoluted way, I think that is true, but a priori, I think it's not a very obvious thing because the Markov chain condition merely says that the global state is, let's say you have a density matrix over these first 2 rows in the bottom. Then the Markov chain condition would say that this thing, these 2, that thing is equal to that density matrix over the first 2 rows. But what this says is a bit, it's not unrelated, but it says a different thing.
Thank you.
Okay, so that concludes the talk. And I just wanted to mention that this is, I think there's a lot of way in which we can improve this. Currently, the classical version of the solution only involves 4 particles, which is quite reasonable. But in the quantum case, we have this like a 3x3 thing, which is like a bit too much for practical applications. So it'd be good to be able to reduce this further. And also, some of you may know that these states that satisfy a Markov chain condition, you can actually write them down in a certain normal form. And here you have a like a density matrix which obeys Markup chain condition in more than one way. And it'll be good to understand what the normal forms of those things are, so that we can like remove this like a pesky Markup chain condition at least when we're using this for numerical purposes. And the side remark that I want to emphasize, which I didn't have time to talk about, is that you can actually use this area law of entanglement to like rederive many things about topological quantum field theory, and even discover new types of sectors that people didn't know before. So it looks like area law is a very powerful thing, even though it looks like a very generic looking formula. It's actually hiding a lot of interesting physics and mathematics behind it. And I think it's definitely worth pursuing further on on the implications of the area law. With that, thanks for listening.
Thanks so much, Isaac. Are there any questions for Isaac?
So you mentioned that your procedure, it does not matter whether the global state is pure or mixed.
Right, yeah.
Yeah, and I think there have been some solutions, even geometric solutions for the pure finite dimensional case and so on, right? I think pure univariant quantum marginal problem or something like that, where the subsystems are mutually exclusive and so on.
Oh yeah, that is, so let's see, so bosons, that's trivial. Fermions, I think Klyachko.
Yeah, Klyachko and Schilling.
Right, yeah, right, yeah.
Yeah, so do your procedures generalize those, or have you tried applying these to them?
I haven't thought about it very seriously, but I think you need an extra. So I'm not sure if it'll work, because like the approach that I'm using, in some sense, the global state you're recreating is like the maximally, it's like the maximum entropy state consistent with the marginals, and actually that is precisely true. So I guess if you do that, and if you end up having a global state which has like a entropy of 0, then I guess that will imply that the global state must be pure. But in other cases, I'm not sure what it will yield. So at least for like, if your goal is to understand whether there can be like a global pure state, I think maybe this is not the best thing to use.
Okay, thanks.
I do have a question, another question as well. So this, just naively, I was under the following impression. This is the image that I've had, and I guess I was not fully aware of this new developments. And I guess I have to update this picture, but I always thought that this Markov property, let's say tripartite Markov, right? A, B in the middle, and C is relevant in, appears in low energy of local Hamiltonians when the size of B that separates A and C is much larger than the order of correlation length.
Yeah, that's why. Well, actually, so
I mean, if you, yeah, go ahead.
I'm not sure. Yeah. Okay. So
I mean, roughly speaking, that's sufficient, right? Because the correlation functions fall off exponentially. At some point, you're going to be in a setup where your CMI, conditional mutual information, is going to be 0 or near 0. But I'm surprised that this could actually occur in systems where in size scales that are much smaller than correlation length.
Yeah, so maybe
that's surprising.
So I think this is a distinction between the quantum and the classical information, but let me just say that's a very speculative statement, first of all. Perhaps a point that is worth mentioning is that, let's say in this classical case, it turns out that in the classical case, in the many-body setting, like again, what you only need is this. And the point that I'm trying to make here is that the classical solution applies to like a chain of like a 1D classical chains. Like imagine you have like a 1D Ising models, and obviously they can have like non-zero correlation length. And I guess the point that I'm trying to make here is that there are like trivial examples for which you satisfy this this constraint, but the correlation lengths can be larger than the size, the range of this constraint.
So I guess here, what we're learning in this example, one-dimensional example you gave, we're learning that all the correlation we see for regions that are further apart are classical.
In this example,
yeah,
so it looks like
they're non-quantum.
Pascal, yeah. So maybe an interesting question is whether there really is a dichotomy like that. So it may be for classical information, really these like local conditions suffice, but for quantum correlations, maybe you need more. Yeah.
I see. Okay, thanks so much. Are there any other questions? If there are no more questions, let's thank Isaac again for the great talk. And thanks everyone for coming. Thanks, Isaac. Have a wonderful day.
Thanks. You too. Bye-bye.
Bye.